Okay, hello. I think the time is ripe to start with my presentation. So welcome everybody. My name is Boguslaw Cyganek and I'm from Cracow, Poland. I'm with the AGH University of Science and Technology. I do some research in computer vision and in numerical analysis, but also in artificial intelligence. Also, I teach students operating systems, C++. And the title is Beyond the Standard Floating Point Computations, what's new, what's interesting, what's useful. So obviously we'll be talking about computations. And here is the plan. So you may think, well, computations again, haven't we done everything in the area of computations? We are doing numerical equations quite well. We are launching some spaceships, etc. So why we need more computations, or what's going on with that? So you will see that new technologies and the growth of massive data, of processing massive data, is just putting some burden on us, and we have to rethink some computational issues. So the presentation is split into a couple of sections. So we'll start with a brief intro to the floating point IEEE 754 standard, pros, cons, and pitfalls. Although it is not something we are very be going deep into the subject, we have to start from the current point of technology. Then we'll move to the quest for the 16-bit floating point format. Then we'll take a look at the compression methods for floating point data, lossless and lossy, and some libraries and methods which can be used in C++ programs. Finally, we'll take a look at the new proposition of the floating point representation, which is POSIT, which are POSITs, and POSIT arithmetic, and how to use it. And everything will be with examples and how we can use it in C++. So each of this topic is quite practical as well. So we'll go to minimum mathematics, we'll go to practical stuff as much as possible. So we are talking about computations. So for computations, we need computers. Here is one in Cyfronet Computer Center in my city at my university. It's called Prometheus. I put this image because I need this image more than myself with the Prometheus. And look at this for last 20 years, how the computations changed. So computational power, flops per second, is growing from giga to tera to exa, couple of orders of magnitude. So we are doing, I remember being a student and having electronic parts in megahertz. So now we have dozens of gigahertz possible. But at the same time, if we take a look at the memory transfers, they are not growing so fast. Although we live in the era of massive data, of big data production. So we see this discrepancy here. So this, what we'll be talking today, is around this discrepancy as well. So data transfer is a bottleneck at large processing scale. And every bit counts. So all these new technologies I will be talking today about are also just to respond to these challenges. Okay, so how it goes on in practice? Well, we're using C++ for over 40 years, but we have we have many practical examples like this one taken from my classes. And okay, we have a slider for some graphical user interface. We wish to compute something, and well, whoops, we have a problem. So this is a first example on the first pages for beginners. So what do? Well, we just change int to double and everything works fine. Well, maybe in this case is not the bad idea. But what about massive data? What about if we compute, for example, some filtering, and filtering is done by convolutions, and convolutions require some fractionals. So if we just like this, change pixel values to double from byte to 8 bytes, for example, what we do with our data stream, we are multiplying it. Sometimes it is justified, but not always, and we have better ways to avoid it. So new technologies are just requiring new tools and new approach and new thinking to computations as well, and to representation of objects. So let's go to the first let's say subsection, brief intro to IEEE 754. We all know this. If you are interested in some refreshment, so I can recommend my talk from last year, CppOnSea. There is more going into details, into bits, but especially how to compute, how to compare the numbers, how to divide the numbers. So I will only briefly sketch today what are important results of this refreshment, which are important to understand POSITs or fractional compressions. So, well, we have the standard since 1985, but there were times before that. So once upon a time in a galaxy, there was no floating point standard, and people lived there as well and did computations. But computer used many different representations for floating point numbers. And the lack of a standard was a hard problem by the early 70s for writing and maintaining code. Also, each major company had its own standard or variant of a standard, and this differed in the word size, representation, rounding behavior, general accuracy of operations. The basis of computations were 2, 10, 16. So compatibility across multiple systems was in desperate need of standardization in early 1980s. And indeed, this happened. And this happened mostly thanks to the Professor Kahan, who wrote this paper in 1981, Why Do We Need a Floating Point Arithmetic Standard? Here is the paper, if you are interested, quite well written and interesting to read even today. So I will only cite the beginning and the end of this paper. So he wrote, numerical software production is costly. We cannot afford it unless programming costs are distributed over a large market. This means most programs must be portable over diverse machines. And also, we need an abstract model of their computational environment. We need something simple, or if not so simple, not so capriciously complex. However, at the end of this paper, he finishes like this. Alas, the proposed IEEE standard for binary floating point arithmetic will not guarantee correct results from all numerical programs, but the standard weights the odds more in our favor. And indeed, for these years, 30 years or more of the standard, well, we can see that there is a gap, but the standard paid off. We all are using this standard, and the software is is portable among systems. Okay, so let's start with the bit representation of floating point values. So as you know, there is sign magnitude standard, so the separate bit for the sign, separate q bits for exponent, and this is constant value, what is important. But there are variants naturally, which we will come to in a moment. And there is this mantissa called also significant or fractional part containing p-1 bits in the word, because one bit is special. I will come to this in a moment. So the standard defines many floating point formats from which the single precision, double precision are probably the most common. We have float and double basic types in C++. Single precision, float 4 bytes, 8 bits for exponent, 24 bits for significant, mantissa, and double is 8 bytes, 11 for exponents. Certainly there is a sign. We have also not very common 10 bytes, 80 bits standard. Sometimes on some systems it is long double, and quadruple precision, 16 bytes with 113 bits for fractional is sometimes also like long double in some systems. But on the standard requires only that long double is not worse than double and so on. But recently, and the standard was improved after the first release, after a couple of years, the half precision was added. So it is going slightly in counter direction because, well, we would expect, okay, we have bigger machines, we need more precision, we need more dynamics for data. So we're just devising longer standards, but we go the other way. Why? Because of this this diagram with data transfer, which I showed, because of data bottlenecks. So we are producing more data, and in many cases, half precision is what we strive for. For example, in deep neural network training, as I will be talking about in a moment. So once we have this representation, its value is can be read like this from this formula, and we have the special D0 bit which does not need to be stored, and we have the constant base, which is in the standard IEEE standard is 2. Sometimes it can be 10 for some special cases, and we have this exponent, so the formula is like this, quite simple. But we have some peculiarities, I would say. For example, exponent is just from E minimum to E maximum. It is biased also. Mantissa is computed like this with this special D0 bit here. So let's take a look just with a small experiment. If we put only 3 bits for mantissa, and we have -1, 0, 1, 2 possible exponents, and the base is 2, and if we generate the values for this possible combinations and complying with the standard, we have such a representation. So okay, we know that the value of the value is given by this formula. So what we can find out? We see quite easily that floating point values, which are shown in red, group themselves, concentrate in the groups in accordance with the number of exponents. So we have 4 groups here, which correspond to all these values of exponent. Well, but most striking is that spacing within a group is the same, but the spacing increases with increase of exponent. But most striking thing is certainly that we have gaps in this representation. So no matter how many p we'll take, we'll always have gaps when going from a real representation, even from the distance from 0 to 1 of real values like they are defined in mathematics, when going to this representation. So we always approximate. So vast majority of values are just the closest, which are the closest red points in this example. So this simple model just is useful to understand what we are dealing with, and also because the representation is in the normalized form with this leading one, we have a problem representing values close to 0. Certainly 0 can be albeit set to 0, and but with this sign magnitude we have actually 2 zeros, but we have problems with values close to 0 as is visible in this plot. Okay, so in FP domain, many, I would say majority of real values cannot be exactly represented. So we need some rounding, but rounding makes a round of errors, entails some special actions. So the result of this is that some mathematical laws don't hold. For example, like commutative law. So this means that the order of addition matters. Floating point representation of number is not unique. For this reason, we have this normalized form, but as I mentioned, but we have a problem near 0. So we need this special case of so-called the normals symbols. And we have this bias of exponent, which doesn't help, but the bias is to avoid negative values encoded for the exponent. And as I mentioned, this special D0 bit is so-called hidden bit, and because it is in the normalized format, it is always 1. We don't need to store it, so this is called a hidden bit trick. Well, standard requires at least precision as float and long double as respectively. But there are also some special values which are especially encoded. So there is a positive infinity, negative 0, positive 0, and not a number. This is quite interesting in the light of what we will be talking about new formats, because this special bit assignment to represent not a number. What is not a number is for example value of square root from negative argument. So exponent values of all ones represent this not a number. But what with the rest bits? Because exponents are only part of the word. So we see that there can be some room for improvement, not to waste so many bits. And the significant exponents are especially encoded to represent the above special values. For other than above, a value 127 in a single and 1023, double precision is added to as I mentioned, to avoid direct negative exponents. Well, yes, and we have problem with this special group of very small values, the normals, to such an extent that they, in many cases, they are not supported in hardware, and they need to be emulated in software. This is especially painful in embedded systems. So some people scale the values by 0.5 to avoid computations in this region of subnormals. And also we have defined mathematical operations, and rounding is inevitable if the result cannot fit in the FP representation due to an insufficient number of bits for precision. And there are 5 rounding modes: default around to nearest, so the nearest value is chosen, and this is the default rounding, but optional around to nearest, around up toward plus infinity, around down toward minus infinity, around toward 0, which means a cut of fractionals, which is the default rounding for integers. And here are some examples which, well, just to show how we operate. So this is the negative value with -1. The exponent is 127, and the value of mantissa is 0. Because it is biased, so we subtract the minimum exponent. So we have 0 here and 0, and we have this hidden bit. So altogether make the value of -1. 0, 1, for example, cannot be represented exactly. So we have an approximation here. The exponent is 123. The mantissa is with these bits. We add the hidden bit to the front, and then we have this approximation. So these are standard operations. We can find the minimum value, which is like this, because all zeros in the exponent are reserved for 0. So minimum value will require at least the one minimum in the exponent. So here is the value of a minimum. The same, and this value can be found out by calling numeric limits of float. We have also maximum here, but what is important here to notice is that almost all bits of exponent in this middle part are filled with 1s, and if they are filled all with 1s, this means not a number. But if we have not a number, then all bits of mantissa are just payload. So this is the room for POSITs, as we'll see in a moment. So here is also we can call max and find out this value. So just to summarize the basic facts about the floating points, we always work with approximation of real values. Computations can result in overflow, underflow, and are burdened by round-off errors. Commutative law doesn't hold, so order of additions does matter. This is especially true if we are using accumulate. So this is the subject of my previous talk. How to sum up the values, use the Cracow algorithm, or sort them first and then sum up, or use the special library if you wish to avoid big errors. And there is a very important value of machine epsilon, which is a difference from 1 to the nearest positive value. So this distance is called epsilon. And adding values with different exponent leads to large errors. Subtracting close values can lead to severe cancellation errors. So such results, which you can find more details in my presentation and in my book. Also, so if we are comparing to FP value, we need to scale epsilon by maximum of this value, and this is the threshold. So in other words, we cannot compare if we are too close. If you are in the gap, then the values are the same. So if we are doing some iterative processing, also we have to take care, normal thing, but when dividing the values. So C is a result of A divided by B if A is equal C times B. So to achieve this, we need to pose some requirement either on A max, and then we can find out the minimum value of a divisor, or do vice versa. And all these values can be worked out from this minimum, calling this numeric limits for T being a floating point type, like float, or we'll see in a moment some examples. Okay, so now let's go a little bit to some improvements of this standard. The quest for a 16-bit floating point format. Why we need it? Well, in 2008, a revision was made and binary 16 was added to the IEEE 754 standard. 1 bit for the sign, 5 bits for the exponent, 10 bits for the significand, plus certainly the hidden bit, which is always 1 for the normalized set of values. There were many custom versions of 16-bit float because it was necessary in many computations. NVIDIA and Microsoft defined the half type in CG language before the standard was updated to binary 16, implemented in silicon by NVIDIA GeForce. Graphic cards also used in computer graphic formats, MATLAB, OpenEXR, JPEG, and so on. And you can find many examples. But as I mentioned at the beginning, having many variants is not very beneficial because we are not compatible. So at least we know that IEEE standard for more than 10 years has binary 16 as well, so we can use it, but it is not the standard type in C++. So adding a fundamental type named short float to the C++ standard was proposed by Boris Fomichev and the group of collaborators. But the question is, will it be accepted? I don't know. So you can find out more reading this note. Also, GCC supports half precision for certain platforms like ARM. Well, but this use is limited to this platform. But finally, we have what I am using is the nice library developed by Christian Rau and released under MIT license, and is simply called half. And it has some benefits, as I will mention in a moment, and is IEEE 754 compliant. So let's look at the examples. So to use half, we need to hash include half HPP. This entirely header library. We can make an alias like here, and we can play with some computations. So for example, we defined an object R like radius. Well, we will need pi to compute some areas, and we can compute the area of a circle like this. And so the result is 462.25. Well, here we see that we convert. We use the converting constructors to convert from doubles or floats. It's also possible, and this constant doesn't look nice. So fortunately, we finally we have constants in C++ 20. For this purpose, we need to hash include numbers, and then we can at least try to write something like k pi h for half, stud numbers pi underscore v for the half type. Unfortunately, this doesn't compile because half is not yet compliant with this new library because it is quite new, C++20. But we can make some workaround this problem and call arc cosinus from this value and have pi defined this way. But anyway, this numbers with constants is quite useful and also writes into unifying our software. So it is a good idea to use it. So to compare computations with half and with float and double, we can define pi for float and double. Certainly they can be const or const exp in this case. And we can compute area like this from the previous with the same like previously used radius values and here. And if we compute them, we can compare what is the difference. So we see that there is no difference at least to 3 digits after a digit for float and double, which might be sufficient for us in this case. But for half, it is 0.006, let's say, rounding the error. So is it big or small? Well, depends. But the thing is, we need to control precision and dynamics all the time. So this is the take on from this talk. We need to control precision and dynamics, whatever we are using. Okay, so to control precision and dynamics, it is good to have some tools. And as I already mentioned, there is this numerical limits library in standard library. So we can write such a helper template function. So for any type FP, we can take its name because we don't know what will be substituted here. We can type it just for reference. So this is the way I found to type a name of a template type, but maybe you have better ideas. And we can display some important parameters like epsilon, radix, base, digits of mantissa, a minimum, maximum value. If the type has the normals, the normal minimum, lowest value has infinity and rounding style. So with such a helper, we can examine our half library, and we got this. So the epsilon value is like 0.009 in this case. So again, is it sufficient for our computations? Depends, heavily depends on application, but the thing is we need to control this. We see radix 2, mantissa 11, but look at the max value is not that big, 65,000. In many applications, well, probably it is not sufficient. So if we run FP limits for float, we have much bigger maximum value, e to plus 38, and certainly the values are even much bigger for double type. Okay, so let's finish with half library and with this topic. So pros are conformance, standard conformance, that's good. A header only library, that's also good. Numeric limits aware, hash aware, well documented, MIT license, very good. But there are some cons, so slow, no hardware support. So this is the problem while going far away from the standard, but is something also important when doing mass computations. If we have a smaller memory footprint, but how does it affect the computation time? Less memory, good, but no hardware support. So another take on measure the time, because it can be some interplay of many factors. No const exp yet, non-stud numbers yet. Alternatives, NVIDIA is doing big progress in mixed precision programming package, mostly for CUDA and for deep learning. There is FlexFloat, also interesting software library proposed recently. Brain floating point, bfloat 16 by Google for tensor processing units. Intel FlexPoint, and you can find references here. But also you can use stud ratio if, well, in some computation. Don't forget you have it. And don't forget you have fixed point arithmetic. Well, you can use my class FX4 from the examples from the book on C++, but there are also other libraries for fixed point arithmetic. But again, measure and control dynamics and precision. Well, a lot of research into deep learning is still ongoing. So, okay, let's move to another subject, which is quite interesting, floating point compression. Well, we can be tempted to run some ZIP, Lempel-Ziff algorithm on floating point values, but and to achieve some lossless compression, but it doesn't work because of the entropy and the structure of this data is not working well. But there are many interesting approaches to lossy compression. One called ZFP, probably from zip floating point, was proposed by Dr. Peter Lindstrom in his paper from 2014. And his primary application was computer graphics. So even in this shot of his paper, we can see some examples of renderings on compressed double precision floating point data on a 3D grid. And he claims that even for 4 bits per double compression, 16 times compression, the image is visually indistinguishable from a full 64-bit precision. Well, that's probably true due to many factors, or also to the precision of monitors. But there is a question if we apply this technique to some real computations which we depend on. So, for example, some physical emulations or machine learning, etc. So, but the answer is yes, and I will show in a moment. So, how does it work? The main observation is that the multi-dimensional data, like tensors or images, videos, the local subcubes, the local neighborhoods of elements are quite similar. Especially similar in the exponent. So the obvious compression mechanism is just to take off the common exponent, and we have some kind of compression. But as you will see, it's not that simple to work in many cases. But this autocorrelation and similarities is the principal assumption. So this works in multi-dimensional data. So the key point here is to use multi-dimensional data, where the neighborhood, if we have pixels of a sky in a video for a long time, probably they will keep the similar values. And this is, for many years, it is used in computer graphics and computer vision. This observation here, it is used to compress floating point values. Okay. So how does it work? The method maps small blocks of 4 to the power d values in d dimensions to a fixed number of bits per block. So for 3D, we have blocks like 4 by 4 by 4. And each such a block is stored using the same user-defined number of bits. Each block is compressed in 5 steps. So details you can find in the publication. You have below the name of this publication, and there is a lot of mathematics. Maybe not a lot, but especially with some transformations. So first thing is align blocks of value to a common exponent, as I mentioned. The second thing is convert this floating point number to fixed point representation. The third is to run an orthogonal block transformation to decorrelate the values. Quite common operation in many compression schemes, also like JPEG with the cosine base, and this is quite interesting. So for details, formulas, just please refer to this to the paper by Mr. Lindström. Next step is order transform coefficients by their magnitudes, and then encode the coefficients 1 bit per plane at a time. And the thing is ready to read and write. Accesses can be random to compress data. So you will see in a moment some examples of using this scheme and the C++ wrappers to the multi-dimensional vectors operating in accordance with this algorithm. So what is so characteristic to the ZFP library? You can certainly download it from the GitHub, and there is a C++ wrapper to the compressed array primitives. They can be used like any normal stud vector. There is also an interesting mechanism of cache to optimize the frequency of compression and decompression when updating the blocks. Well, the thing is, also as I mentioned, is the library is limited to regular gridded data. So then we benefit if these local neighborhoods are really similar. So if we generate something irregular, then results can depend. Applications certainly in computer graphics, but also in scientific multidimensional data analysis, as I will show you shortly. There are 5 compression modes: expert, fixed rate, fixed precision, fixed accuracy, reversible, which is lossless. The library also operates in parallel. There are different APIs for C, bitstream, but also compressed C++ arrays, what we are mostly interested, at least myself. As I mentioned, the arrays can substitute stud arrays. However, there are some limitations. I will not address them here because, well, there is a mechanism of compression, decompression going on and all these discussions. But each multidimensional array can be processed as a linear buffer. So also can be approached as multidimensional with special iterators. Some symbols like not a number are not supported. There are 6 classes for 1D, 2D, 3D arrays of single and double precision. And finally, the example. So we need to include ZFP array, for example, 2 here. And let's make one stud vector array at the beginning, just to compare, not yet compressed. Let's make a random engine and real distribution from -123 to +123 dynamics, and generate, populate this CPP array with random values here. Okay, this is this code, and the code for using ZFP is like this. Here we have an object of array 2D, also with the same number of columns and rows, but there is this parameter of rate, which tells how many bits per value to store in the compressed representation. So you can play with this. 4 by 4 is okay. For some reasons, this is, well, there are many other parameters as well. And this is not default. So we have the same size, but we can operate like with any other array. So we can just copy from CPP array to my ZFP array here, no problem. And we can, for example, compute mean square error with stud algorithm, transform reduce. By the way, this is quite interesting function. if you haven't used it, just try to play with it. So we start with CppOnSea, and with my ZFP array, we start with double zero value, and we have two functions, one for reduction and the second for transformation. So on each step we'll compute the square of the differences of each element. Then the squares are added, and finally we can compare the size of original in bytes and of this array. Let's do some computations. We compute the square root of the difference, and the results are like this. So interesting thing is that with the compression 73%, we have MSE 0.63 for this range of minus 123 to 123. Is it good or bad? Well, depends. But in many cases, such compressions are worthy considering. But well, let's control the precision and dynamics. Alternatives, hardware implementation, but only FPGA. So written in System C. So this is what I'm mentioning to the students, so that this is worth learning C++ and C, because they can be also used in hardware programming. There is another SZ library, if you are interested, a little bit different, used for deep learning. Alternatives, we use that library in our system for data compression. We use tensor decompositions like this. So if we take a multidimensional cube of data and we decompose it in some way, the decomposed parts are more or less weighting in the number of bytes than the original data. So this is the way of compression. But after that, because we need to compute in floating points, we apply this ZFP library with good results. So I can recommend this. If you are interested in tensors, decomposition, things like this, so I wrote a book 10 years ago, so you can try to find some details. And finally, we have this new format, a new kid on the block, POSIT arithmetic, something totally new, not half, not IEEE. So developed by John Gustafson as a direct replacement for IEEE. Standard POSITs provide compelling advantages over float. And here is the paper by Gustafson and Yonemoto. Larger dynamic range to the variable length encoding of exponent. Well, this is the key difference. In IEEE standard, the exponent number of bits for float or double, okay, this is different, but for a given type is constant. So, but sometimes in practice, we don't need such big exponent. We would like to trade it off for precision. Well, having double, it is not possible. I need to keep this bits all the time. But in POSITs, this is dynamic. So this is the primary modification. More fraction bits if small exponent is sufficient. Never overflow to infinity or underflow to zero. This is a big subject of how underflow and overflows, but the POSITs behave more naturally here. Not a number. There is no bit representation from not a number. This is a situation which happens if happens. So it can be processed by an interruption. So more concise bits assignment. So what we are using here in POSITs is this dynamic size of exponent and fractionals, but also we take advantage of these extra bits which are reserved for not a number in IEEE standard and which are just waste of space in many cases. And POSITs environment mandates the fused operations. So the fused operations means that the rounding is at the very end of the compound operation like multiply and add, mult or sum of dot product, etc. So this is very beneficial. So let's start with IEEE standard. So what the difference? Here is the difference. we have we split the exponent from the ItripleE into regime bits and exponent, and we have this fractional or mantissa like here. Okay, what is more? This can be even 0 bits. So look at this. So n bits is constant. The word, the length of a word is constant. But then we can play with this regime, exponent, and fractional. So regime is a number of bits for a regime is a parameter here. But exponent can be from 0 to some number of bits, just to fit into n bits, and they exchange the room with fractionals. So here we have ES bits, the number of bits used for exponent. And if for IEEE 754, the formula was like this. So for the POSITs, we have like this. So you see, especially the difference is in the exponential part with this scaling component. You see it to the power of k. And base to exponent is like it was, but now the situation is different. So the formula is like this, but also the format is complement to 2, not sign magnitude, like in IEEE. So this is for POSIT. And here is the complete formula. So we have only 2 special bit encodings, zeros for 0 and first 1, and all zeros for plus, minus, infinity, and all other combinations are used to store in a dynamic way my values for computations. This is the virtue of POSITs. The rules different, as I mentioned, so already mentioned that 2's complement. So let's go to computations. Let's go to computations. Regime bits, the number of k used in this UC to the power of k is determined by the round length of the bits. And this is done computing how many the same bits are in the row up to the first transition. So here we have 4, non-transition, 3 and transition to 1, 2 and transition to 1. X means don't care. And here we count number of 1s and transition to 0, and the rules are 2. If bits are 0, then this is minus number of bits till transition, and if they are 1, this is m minus 1. So here we have 4, so it's minus 4, 3 minus 3, 2 zeros minus 2, and here we have, for example, 2 1s and 0, so we have 2 minus 1 is 1. So this is the value of k. And so this is the regime value you see to k, which is 2 to the power of 2 to number of bits in ES, number of bits in exponent. It can be even 0, we will see in a moment. So this USEED value, so we know the k value, now USEED value is 2 to the power of 2 to the number of exponent bits, which can be 0. Then we have 2, 1, 2, 3. So this USEED can be even such a big value for only 4 exponent bits. So it scales with a number of exponent bits from 0 to some dynamically growing value. Exponent is regarded as assigned integer, non-bias. Can be ES exponent bit, and this format is so-called tapered accuracy. Numbers near 1 in magnitude have more accuracy than extremely large or extremely small. Because time is passing quite quickly, I will go a little bit faster. There is no subnormals, no exceptions. You will see in a moment in a plot. But take a look at 3 bits POSIT here. So we have this, you see it is 2 to the power of 2 to 0 is 2. So we have exponent 0 bits and fractional 0. So we have only 2 bits of regime and 1 bit of sign. So we have 8 possibilities. We can draw them on the horizontal line. But what is more intuitive is like proposed in the paper by Gustafsson, is to put the numbers on the semicircle. Sorry. So what do we have here? First we have 1, 0, 0, so this is infinity, and 0 is 0, so we have 3 remaining values. So for that one, we have 2 ones till transition. So 2 ones minus 1 is 1. So k is 1. So here we have UC to the power of 1. Here we have k is 0. So we have whatever you see this is 1. And here is minus 1. So here we have reciprocal 1 divided by the UC. Extending values of POSIT precision increasing by appending bits, and values remain where they are on the circle. When a 0 bit is appended, the value are the same. When 1 is added, new values are created. And there are special interpolation rules, which are not very complicated. I cited them here. But anyway, the intermediate values are computed either as geometric mean or as arithmetic mean between the numbers. So here is the example. The example works best for posits from 3 to 5 bits and 2 bits for exponents. So we see this 16, and we have such a values. So this is for 3 bits, this is for 4, and this is for 5. So if we take a look, for example, from here, we have 1, 16, and then we go to the intermediate value, we see that this is geometrical mean. 16 times 1 is 16, and square root is 4, and so on. Also, and we can go like this. So details you can find in the paper by Gustafsson. And here is an example. So we have sign, regime, exponent, fraction. So you see here is the sign 0. Regime bit is 256 because you see it is 2 to 3 because there are 3 exponent bits. So it's 256. And we have 1, 2, 3 till transition to 1 in regime bits. So we have -3 times base, which is always 2 power of 2 because exponent is 2. And we have this value, which is 153 and by 256 because this is 1, 2, 3, 4, 5, 6, 7, 8 values plus this hidden bit. So it gives this value. So that just an experiment. So summarizing, word lengths of IEEE and POSITs fixed, but inside we have differences. So we have two's complement in POSIT, we have variable length, non-bias, we have variable length for mantissa, we have only one infinity, we have only one not a number and not represented by bits, we have gradual, natural, underflow, overflow, only if we divide by 0 is infinity, so this is called natural. No exceptions, no subnormals, and many bases, not only one. And here is, let's go to the software. Finally, there are few POSIT implementations, Stillwater, beyond floating point, but what I found the best is this CppOnSea, used also for convolutional deep neural networks, and also you can download it from the GitHub. Let's see how does it work. We need to hash include POSIT 12 in this case and see some examples. So we create POSITs, number of exponent bits is 2. We create one value 20, 1 minus 10, and to display them, we need to cast them to float, for example, or we can just reciprocal compute as well, casting to float. And the values are like this. So we see this is not 0, 5, but 0, 0, 4, 9. But remember, this is only 12 bits. 12 bits, a little bit more than than a byte, well, 50% more than a byte, but less than 16 by the same amount. So it's not bad. If we make the same for B, we obtain these results. And now we can compute some values, A times B divided by A. But let's go to our area example. Here we compute our area and we compare with the floating point value. So here is the result. There is a difference. So let's measure the difference. So difference is 1% of accuracy, but 62.5 data compression. So that's the point. But we must always control dynamics and precision. So for this reason, we have numerical limits for POSIT, so we can read out minimum, maximum value, epsilon, like this. And well, we are almost done. Time is already done. So here is the literature. You can find it on Wikipedia. It's great, we have it. So let's donate it. Wikipedia is the primary, also the seminar work by Donald Knatt, by Professor Kahan, Gustafsson on POSITs, Elias, some other paper on coding, Goldberg on computations on floating point arithmetic, some libraries, the standard, if you wish. There are also libraries for arbitrary precision arithmetic. I wasn't talking about this, but it's good to know. And the paper Fixed Rate Compression by Peter Lindström is here. You can find out also our papers on orthogonal computations, tensor-based compression, but also Introduction to Programming with C++ for Engineers. So conclusions, we are all indebted to IEEE standard. The entire modern numerical world depends on it, but we can do more and we wish. We must always control dynamics and precision of the numbers, no matter what we are using. New technologies launch new demands on data representation. So machine learning, deep learning, big data, data transfer is and probably will be a bottleneck. So new directions, data compression, lossy, that's okay if we measure new formats, but most of all, POSITs. But we need hardware integration implementation, FPGA, but what about processors? RISC-V maybe, direct replacement for the standard. And we are still ahead of having new formats integrated into the system. So what with old software? So that's all. Thank you very much for your attention. And if there are any questions, oh, by the way, there is my book. If you are interested, there is chapter 7 devoted to numerical computations, but also some stuff about programming with C++ for beginners and advanced. So you can download code from my GitHub as well. So thank you once again, and I hope you enjoy.